In this video, we're going to be talking about Edgeworth boxes. So Edgeworth boxes are very exciting. You can see I'm excited about them. The basic idea is that we're going to plot two agents' indifference curves, and we're going to plot them on the same plot. We're going to flip one of them upside down. And this is what's called an Edgeworth box. So we're going to have a look at this with an example, and in the example of two agents and two goods in an exchange economy. I'm going to write the label for each agent in the superscript here. So EA is Ann's endowment, EB is Bob's endowment. Here Ann has 75 units of X and 10 units of Y. Bob has 25 units of X and 40 units of Y. I would point out that means that the total amount of X that is in this exchange economy is 100, and the total amount of Y in the exchange economy is 50. We're going to give them the same utility function, so Ann's utility function is the same as Bob's. It's just log X plus 2 log Y. And let's give it a go. So the first thing to note in drawing an Edgeworth box is that we need the width and the height to be correct. Here, the total amount of X that we have is 100, so we want 100 units across the bottom here. The total amount of Y that we have is 50, so we want the box to be 50 units high. And then we're going to put A, in other words Ann, at the bottom left corner, and B, in other words Bob, at the top right corner. And then what this graph represents is as we move from left to right, we're increasing Ann's consumption of X from 0 all the way to 100, but we're decreasing Bob's consumption of X from 100 all the way down to 0. Looking at the vertical axis, as we move up, we're increasing Ann's consumption of Y, and as we move up, we're decreasing Bob's consumption of Y. Right? So Bob wants to be to the left and down, that means he has more, and Ann wants to be up and to the right, that means she has more. Now if we wanted to, we could plot the indifference curves, and that's what we've done here. This red line, let's start with the blue line. The blue line is Ann's indifference curve through the endowment point. So here, this endowment point, we can plot it quite simply. If we just take Ann's endowment point of 7510, we plot that point. That point also tells us Bob's endowment point, which is 25 units of X and 40 units of Y. Let's check back. Sure enough, 25, 40. All right, so if we've done the plot correctly, we could just plot the endowment point for Ann, and it also tells us Bob's endowment. And then here we've plotted the indifference curve for Ann that goes through this endowment. And as you can see, it looks something like this. We've also plotted the indifference curve for Bob going through this endowment, and it's this red curve. Right now, Ann wants to be up and to the right. So anything up and to the right of this blue curve is better than anything on the blue curve. Bob wants to be as far down and to the left as possible, so anything down and to the left of this red curve is better than anything on the red curve. So if we ask this question, is the endowment Pareto efficient, then we can say no for a couple reasons. First of all, remember that Pareto efficiency implies that the two agents have the same MRS at a Pareto efficient allocation. So we could do the math, but it's pretty obvious that the slopes of the red and the blue lines, these two indifference curves, are different through the endowment. Right? These two slopes here are different, so different MRSs. We can also plot a bunch of Pareto improvements. So if we look at this shaded region here, everything in this yellow shaded region is down and to the left of red, so Bob likes it more, and it's up and to the right of blue, so Ann likes it more. Right, so we can conclude from this that the endowment is not Pareto efficient, and there should be some gains to trade if we can get them to move into this region here, the yellow region. So we might ask, well, what points are Pareto efficient? And we can solve for this explicitly. We know that Pareto efficiency with these Cobb-Douglas utility functions is going to imply that the marginal rate of substitution is equal for Cobb-Douglas. So we just plug in the marginal rates of substitution, which is just this for each agent. I'm not going to show you why that is. We've done that plenty in consumer theory. Now, we still have 4 variables in here, which is going to be a bit hard to plot, but we know that we can substitute them out because everywhere in the Edgeworth box, by feasibility, what Bob has of good x is just 100 minus what Anne has of good x. And what Bob has of good y is just 50 minus what Anne has of good y, because there's a total of 100 units of x and 50 units of y. And so what we want to do is just plot this for one of the people. It's always easier to do it for Anne. So we're going to substitute out these xb's and yb's. So we're going to plug in this xb here. We're going to plug in this yb here. So 50 minus ya goes in there. So this gives us something a little bit ugly, but if we do the algebra, it ends up being not ugly at all. We just get ya equals xa over 2. And if we plot that curve, it gives us the set of Pareto efficient points, which we call the contract curve, right? This is defined as the contract curve. So here it is. Ya equals xa over 2 is its black line on the diagonal. Now the contract curve won't always be the diagonal between the two corners. Here it is because they have the same utility function. Right? There's some symmetry going on here. So any allocation on this black line is Pareto efficient. In particular, any allocation between this red line and the blue line, and also on the black line, is both Pareto efficient and preferred by both agents to the endowment. So now we want to solve for equilibrium. Part of the beauty of Edgeworth boxes, it's about as simple as a problem as you can have, such that you can solve for the price and the quantity simultaneously. It's a little bit hard, so we'll do it in steps. Step 1 is the easiest step. What matters in a market is not prices, but relative prices, and therefore we can always just normalize one of the prices to 1. You could also normalize the price to 2. You'd end up solving for the same relative prices. Do not normalize a price to 0, because then you'll end up dividing by 0 and crappy stuff will happen. So always normalize a price to 1. Then we find income. So we find the W's for each of these agents. Now so far, when we did consumer theory, I just gave you the W's. Here in these exchange economies, though, they don't have incomes per se, but they do have their endowments, which are going to be worth the money as an income would be. And so we want to express these in terms of the endowments. So agent A's income is just going to be the price of X times how much A has of X in the endowment, plus the price of Y times how much agent A has of Y in the endowment. Here we've normalized Px to 1, and Anne had 75 units of X, so this is 75. And then we don't know what Py is yet, but we do know that Anne has 10 units of Y, so this term here is 10 Py. Bob, on the other hand, had 25 units of X and 40 units of Y, so here's his income. So we have incomes as functions of Py here. Now, there's a little trick here. It's not difficult to derive. But if someone has a utility function that is a log x plus b log y, and they have income w, then it turns out their demand for x is a over a plus b times w over px, and their demand for y is b over a plus b w over py. Now I would note, a and b here are just numbers, two positive numbers. Right, they are not anything to do with Anne and Bob. These are little a's and little b's. Anne and Bob are using capital letters. Okay, so these are just numbers or just coefficients. In particular, in both of our agents' utility functions here, a was equal to 1 and b was equal to 2. And that's how we had log x plus 2 log y. This will save us a little bit of time. To derive this, it's very easy. You just need to take this utility function and use the 2 golden rules, and you'll end up with this. With these formulae. So step 3 is to find demand functions for y. So we're finding demand functions for y because we've already chosen the price of x, and what we're trying to find is the price of y. But to know the price of y, we need to work out the demand for y. Okay. So demand for y, we know it's b over a plus b, w over py. So for Anne, that's b over a plus b. For both of them, b over a plus b is 2 over 1 plus 2, so that's 2/3. And then w for Anne, we saw in the last slide, was 75 plus 10 py, so we divide that by py. For Bob, again, b over a plus b, this was 1 and this was 2, so this is 2 over 1 plus 2, so 2/3. But Bob's wealth, or his income, was 25 plus 40 PY. So that's what's up here. Divide that by PY. So this gives us demand functions for Y for Ann and Bob, each as a function of the price of Y. Step 4 is that we use market clearing, which means supply equals demand, to find PY. Here, the demand for Y is the thing that we just solved for, these two numbers, YA and YB. And the supply for Y is just the endowments, which was a total of 50, 40 plus 10. This was 10, this was 40. So we just need to solve this ugly equation for PY. We do that, we get that PY has to equal 4. So now we've worked out the price of Y in this market. It's 4. It's 4 times as valuable as X. Remember, PX was equal to 1. Now that we know the prices and the utility functions, so we have everything we need to find demand, we just find, we can find it just for Ann because Bob gets whatever's left, right? If we're working out the optimal bundle, if we know it for one person, the other person is just getting the rest. So we just need to plug PY equals 4 into the demand function for Ann. This is the thing we had earlier, the 2/3 75 plus 10 PY. We're going to plug in 4, so this becomes 75 plus 40 divided by 4. Solve this, we get 115 over 6. And then we're going to plug this YA and PY into the budget constraint for Ann to get Ann's demand for X, right? Ann's expenditure on X plus her expenditure on Y has to equal her income. We know the price of X, we know the price of Y, we know how much Y she purchases, and we know her income, so we're just plugging in these numbers. Right? So the price of X is 1, price of Y is 4, YA we solve for is 115 over 6. WA here, she has 75 units of X, which has a price of 1, and she has 10 units of Y, which has a price of 4, so this is her income. We solve this for XA, is 115 over 3. And so finally, we can plot the equilibrium allocation. She chooses to purchase 115 over 3 units of X and 115 over 6 units of Y. And so we plot that. It's this green point here, 115 over 3, 115 over 6. Of course, by plotting her allocation, we've also plotted Bob's. It would be 100 minus that number for X and 50 minus that number for Y. And as you'll see, not surprisingly, that the optimal allocation, the one that would be reached by the market, is actually on Ann's budget line. So this is actually both of their budget lines. Now note that we could not have drawn this budget line earlier because we didn't know the price of Y. We didn't know the prices. Once we know the prices, we can draw the budget line, and this is what it would look like, and it would be the same for both of them. And it's at the unique point where it crosses the contract curve, which was the set of Pareto efficient bundles. So basically what we've done here is we were able to solve for the price and quantity simultaneously in this market. So first we just normalized the price of X, we set it equal to 1. Then we worked out what their incomes were. Let's go through this step by step. So we just normalized the price of X to 1. We worked out what their incomes were as a function of Y, because we haven't, PY, because we haven't solved for the price of Y yet. Then we worked out the demand functions for Y, again as a function of PY. Once we know those demand functions as a function of PY, we know those have to equal supply for the market to clear, and so we use that condition to work out the price of Y, PY. Once we know the price of Y and the price of X, we can plug those in to work out what the incomes are, and then it's just a standard utility maximization problem where they have to work out how much X and how much Y to consume, although we've already done some of the work for it. So we just plug in the price of Y to the demand function for Y. It tells us the quantity of Y. And then if there are a few different things we could do here, but what we chose to do is plug it back into the budget constraint for Ann, and that gave us how much X she was going to purchase. Then we had Ann's allocation, And then Bob's allocation just had to be 100 minus this and 50 minus this, and we plotted that point here, this green point. So we worked out the market equilibrium in an exchange economy with two goods and two people. As you can see, in the end, Bob ends up getting a little bit more of each good than Ann does. So Bob was a little bit relatively more wealthy than Ann in this problem, which is interesting. You might say that, let's see, if we go all the way back to the beginning, Ann had more total goods. She had 85 total units of goods. Bob had only 65. But importantly, Bob had 40 of the good that was more important, right? Why was more important? Because it had this 2 out front. So Bob ended up being doing better off than Ann. So there we go. We've solved for the prices in this exchange economy, and we've solved for the final allocation in terms of quantities.